students, today I will start the new chapter, heat exchangers. Heat exchanger is a device which is used for the transfer of the heat between the two fluids, usually from hot fluid to the cold fluid. Okay, there are devices which we are going to use for transfer of the heat between the fluids, hot fluid to the cold fluid. Those are called as a heat exchangers. Examples of the heat exchangers are the automobile radiators, cooling towers, like that. And here first we have to take that what are the different classification of the heat exchangers are there. Then later the different types of the heat exchanger also will discuss and will go for the analysis of the heat exchangers. The classification of the heat exchangers. The heat exchangers are classified based on the following considerations. First one, the transfer heat based on the transfer process, that is the heat transfer process. These are classified as a direct contact and indirect contact heat exchangers. Direct contact heat exchangers means the two fluids in which heat is to be transferred, those are comes contact with each other. Okay, these are called as a direct contact heat exchanger. The fluids are coming directly contact with each other to transfer the heat. This type of heat exchangers are the cooling towers, jet condensers, and for water vapor, water spray, etc. Indirect contact heat exchangers means here the two fluids where the heat is to be transferred, those are not coming contact with each other. Those are separated by an impervious surface. There is no mixing of the two fluids, so only the heat exchange takes place. And this example for this type of heat exchanger is automobile radiators. Based on the compactness means we are going to measure the area of the heat exchanger to the volume of the heat exchanger. Okay, the area of heat transfer area of the heat exchanger to the volume of the heat exchanger. Here the one factor we have considered, that is any one side surface area is about 700 meter square per meter cube is known as a compact heat exchanger. Okay, the surface area is more for the same volume of the heat exchanger, then that is more compact heat exchanger. Okay, if it is greater than that one, whatever the 700 meter square per meter cube, that is a compact heat exchanger. Okay, then the size for the same volume, its size if it is lesser, then that we are going to call as a more heat transfer if it is taking, then that we will call as a compact heat exchanger. Then based on the construction, here the tubular heat exchanger we are going to consider. These are also called as a cell and tube heat exchangers. Okay, here the cell and tubes heat exchanger means the one cylindrical cell is used. Inside there is a tubes are passing where the two fluids, one fluid is flowing through the cell, another fluid is flowing through the tube, and that is called a cell and tube heat exchanger. Okay, then second one, based on the construction, plate heat exchangers. Okay, here the plates are arranged in parallel to make a path or a passage to flow of the fluid. Okay, in one passage the hot fluid is flowing, and another passage cold fluid is flowing, where the heat exchange takes place between the two fluids. Then plate fin heat exchanger. Okay, for that plate only, in order to increase the rate of heat transfer, the pins are provided over the surface, that is called as a plate fin heat exchanger. Then tube pin heat exchanger. In the cell and tube heat exchanger only, if we use the pin over the tubes in order to increase the rate of heat transfer, those are called as the tube pin heat exchangers. Then regenerative heat exchanger. Here the regenerative heat exchanger means here the heating elements are used. Heating elements, once the hot fluid is passed through heating element, that will get heated. Then secondly, alternatively, we are going to supply the cold fluid. Then whatever the heat received by the heating element is there, that is transferred to the cold fluid. Like this continuously, alternatively, the hot and cold fluids are supplied to the heat exchanger, where heating and that is heating of the element and cooling of the element takes place. Thereby the transfer of the heat between the hot fluid to the cold fluid takes place, and that called as a regenerative heat exchanger. Air free heaters which are used in the thermal power stations, those are a regenerative type heat exchanger. And based on the flow arrangement, there are four types of the heat exchanger. Four types of the heat exchanger. That's one is parallel flow, and the counter flow heat exchanger, cross flow and multi flow fast flow heat exchangers. Okay, here those are explained with this sketch, all the different types of the based on the flow of the fluid. The first one is a parallel flow heat exchanger. In that parallel flow heat exchanger, hot and cold fluids are flowing in the same direction. Here this is the double pipe heat exchanger. Those are concentric to each other. Okay, in the inside tube, there is an inside pipe, the hot fluid is flowing. Outside, the outside fluid in the this between the two pipes, the whatever the passage is there cold fluid is flowing. Both the fluids are flowing in the same direction. That is a parallel flow heat exchanger. Okay, then here the counter flow heat exchanger. In this, hot fluid is flowing in the same direction, while the cold fluid is flowing in opposite direction to the hot fluid. That is the counter flow heat exchanger. Then cross flow heat exchanger. Here the hot and cold fluids are flowing in the 90 angles with each other. Okay, then those are crossing each other to transfer the heat. Those are called as a cross flow heat exchanger. Then multi fast flow means here in the heat exchanger only once only it will not flows into the heat exchanger. It is a many number of times enters into the heat exchanger and transfers the heat to have the more heat transfer between the hot and the cold fluid. For that, example for the multi-pass heat exchanger is this cell and tube heat exchanger. In this is the one cell pass and two tube passes. Okay, here the through this cell, outside is a cell, through that one only one pass of the fluid takes place. That is in the two pass, that is one enters it is, and again it is crosses and enters into the heat exchanger and leaves from that one. Like that, two passes. Then here two cell pass and four tube pass here. Okay, that is two cell pass. In the cell pass, again once it is passing through this one, passing through like this and enters again into the cell and passing out of this one. Then that is another fluid is passing in one cell pass first, and that returns again through that cell only and enters in the second cell pass, then enters there only, returns and come out from that one. The two cell pass and four tube passes. Then again after that, the classification based on heat transfer mechanism. That is a single phase forced or free convection. Here the single phase, the heat transfer is taking place between the liquid to liquid only. That is a single phase heat exchanger. And phase change due to the boiling and condensation. In the boiling, the heat is transferred from the flue gases to the water. Then the water will be transferred to its phase to the vapor. Then that is the phase change heat exchange. And condensation also, the vapor is condensed to a liquid. That is called as a condensation. Then the radiation and convection combined mode of heat exchanger. That means here the that whatever the boiler only, that is a high temperature flue gases are coming contact with the boiler tube. There the not only by the radiation convection, with the radiation mode of the heat transfer, also the heat is transferring. That's why the combined mode of the radiation and convection heat transfer, that we can call. Okay, like this, these are the different types of the heat exchanger which are commonly used to transfer the heat between the hot and cold fluids. Then one factor we will consider here, that is called as a fouling factor. The fouling factor means wherever the heat transfer is taking place between the hot and the cold fluid, when that hot fluid and the cold fluid flows through the tube, the contaminants present in that whatever the fluid is there, those will be deposited on the surface of the heat transfer. The deposition or accumulation of that whatever the contaminants are there, those will add the resistance of the heat transfer through that surface of the tube, and that whatever is formation of that deposition is there, accumulation is there, that is called as a falling over the surface of the heat transfer of the heat exchanger. And that falling whatever is there, for that while designing the heat transfer equipment or a heat exchanger, we have to consider that factor also. Then the heat exchanger is to be designed, and that's why here that falling factor is also considered for the analysis of the heat exchanger. Okay, that is additional resistance is to be added for the heat transfer. Then that falling factor may be due to the effects, may be due to the higher size is required. Due to that one, cost will be higher. The thermal efficiency will reduces. Periodic cleaning is required. During periodic cleaning, the shutdown is where the shutdown takes place, where the production loss also takes place. That falling whatever are there, those are falling will call. The falling will be due to the scaling and precipitation of falling and crystallization of the solution dissolved substances, particulate falling, chemical reaction falling, corrosion falling, and biological falling, solidification falling. Like this, different types of the falling will take place. There is a different types of the deposition or accumulation takes place on the heat transfer surface. The another thing we will consider here, that is overall heat transfer coefficient. This overall heat transfer coefficient we have already discussed while discussing the conduction heat transfer in the first chapter. Okay, for the analysis of heat exchanger, it is necessary to consider the overall heat transfer coefficient, because of here the heat transfer takes place by the convection as well as by the conduction. And already we know that the conduction resistance and convection resistance are to be considered for this one. Okay, here is the one example, the thermal resistance for this, the heat exchanger. Okay, heat exchanger tube we have to consider, and for that heat exchanger tube whatever is there, here the inside one fluid is there, outside another fluid. The inside heat transfer coefficient is Hi, outside heat transfer coefficient H0, and its thickness of the tube is T, and fouling factors we have considered for the outside surface as Fi, inside surface as Fi, outside surface F0, and thermal conductivity of that material is taken as a K, and inside surface area is Ai, and outside surface area A0. And whatever this overall heat transfer coefficient is there, that usually we will consider based on the either outside surface area or based on the inside surface area. Here the based on outside surface area, that overall heat transfer coefficient 1 by A0 R, this is the R is the total resistance, and this we have taken as the overall heat transfer coefficient. And again, if you consider in this one, the whatever the diameters instead of area, you can write the overall heat transfer coefficient equation like this. Okay, and this is available in the data handbook of page number 143 of Hegde and Niranjan Murthy data handbook, and that we can refer. Okay, the overall heat transfer coefficient, not necessary to remember all the things, but you can refer from the data handbook this overall heat transfer coefficient based on the outside surface area and the inside surface area. And here based on the inside surface area, this equation we are going to get. Okay, this equation where the diameters and thermal conductivity all we are using inside, and heat transfer outside heat transfer coefficient we have considered. And another thing, important thing here, if the thickness of the whatever material is there, if it is small and that can be neglected, then the overall heat transfer coefficient based on the inside surface area only, Ui only we can write like this, not U naught. Ui, that is 1 by H naught plus of 1 by Hi. If you take, this is the overall heat transfer coefficient when we have the negligible thickness of the material. Then fouling factors also we can consider. The fouling factors, if we add, then like this fouling factors after addition we are going to get the overall heat transfer coefficient based on the outside surface area. Overall heat transfer coefficient similarly we can have for the inside surface area. Then here we have to, by considering all these things, we have to analyze the heat exchanger. Analysis means here the rate of heat transfer we have to determine by considering their temperatures as well as its overall heat transfer coefficient. That analysis we have to carry out. The analysis of the heat exchangers are to be carried out by using the two methods. One is the LMTD method, that is the logarithmic mean temperature difference method for heat exchanger analysis. Another method is the NTU method, number of transfer units method, that is also called as the effectiveness method. First I will take the LMTD method for the analysis of the heat exchanger, and later after considering this one we have go for the NTU method also. Here the analysis we have to carry out for the parallel flow heat exchanger as well as for the counter flow heat exchanger. Now I will take for the parallel flow heat exchanger LMTD analysis of the heat exchanger. Okay, here we will consider the parallel flow heat exchanger, and temperature profile for the parallel flow heat exchanger is this one. where the hot fluid temperature is decreases from Thi to the Th0, the inlet hot fluid temperature to the outlet hot fluid temperature, where the temperature decreases for the hot fluid, and cold fluid temperature of the cold fluid inlet increases to the temperature of the cold fluid outlet, then for the particular length of the heat exchanger. And at the inlet the temperature difference we have taken as a delta Ti, and at the outlet it is taken as the delta T0. And here the particular element is considered where the heat transfer of the dq amount of the heat transfer takes place for the area of the dA, and where that one the temperature difference will take for that only for the hot fluid as a dTh, and cold fluid temperature difference for that length for that area is the dTc. Okay, then delta T is the temperature difference between the hot fluid and the cold fluid as a Th minus Tc we are going to consider for this one. Then consideration little we will write and go for the analysis for that. The consider a parallel flow arrangement of the heat exchanger as shown in figure. Let A is the heat transfer area measured at inlet in meter square. mH is the mass of flow rate of fluid, hot fluid, kg per hour. mc is the mass of the rate of cold fluid flow, that is kg per hour. Delta T is the hot fluid temperature difference between the temperature difference between hot fluid and cold fluid locally at the particular that elemental area what we consider. U is the local overall heat transfer coefficient between the two fluids in watt per meter square. Okay, here we have to consider, take a small elemental strip of dA, area dA. The rate of heat transfer dQ from the hot fluid to the cold fluid through an elemental strip of area dA is given by. Okay, here for that elemental strip area, the whatever the rate of heat transfer is there, will take as a dQ is equal to U dA delta T. U dA delta T will take this as equation 1. This is the amount of heat transfer for the particular small elemental strip area. Then rate of heat transfer dQ is equal to the amount of heat lost by the hot fluid or amount of heat gained by the cold fluid. Hence we can write, okay, this whatever the amount of heat transfer is there, this we can write in this way by considering the overall heat transfer coefficient here and area, and also we can write as the energy equation in terms of the rate heat lost by the hot fluid to the heat gained by the cold fluid, that is dQ is equal to minus mHCpH dTh. This is the energy equation, mass flow rate, specific heat into temperature difference of the hot fluid, okay, for that elemental length. And dQ, this is can be given as the mass flow rate of the cold fluid and specific heat of the cold fluid and temperature difference for that length of the cold fluid, where dt is change in temperature for the hot fluid and dTc is change in temperature for the cold fluid. Now we can write the temperature difference between the hot fluid and cold fluid, that we can write as a Th minus Tc, and that difference of that temperature, differentiation of that, if you take, that is a d of dt delta T is equal to dTh minus dTc, and here dTh and dTc we can take from the this equation 2 and 3. This dTh is equal to dQ by minus mHCpH, dTc is equal to dQ by mCCpC. That we can substitute in this one from equation 2 and 3. In 4 we can substitute these two. Okay, after simplification we can have minus dQ 1 by mHCpH plus of 1 by mCCpC. Okay, then after that one, this term whatever is there, 1 by mHCpH plus of 1 by mCCpC, as we have taken as a x. Okay, because in all the steps not necessary to write all these terms, okay, repeatedly. To avoid that one, it is taken as the x. D of delta T is equal to minus x dQ. Then where x is equal to 1 by mHCpH plus of 1 by mCCpC. From equation 1 and 6 we can write d of delta T is equal to minus x u dA delta T. This dQ value we have taken from the equation, from this equation. dQ is equal to this, any one we can write that equation, the rate of heat transfer equation, u dA delta T is there, that we can write for this one. Okay, d of delta T is equal to minus x u dA delta T. Then this, if you rearrange this equation, d of delta T by delta T is equal to minus x u dA. equation 7 will get. Okay, in order to get that is the whatever the total temperature difference for this from this small temperature difference, this equation we have to integrate within limits. Integrating equation 6, 7 within the limits. That is, limits are delta Ti and delta T naught. Integration of the d of delta T by delta T within the limits of delta Ti to delta T naught minus x. This is 0 to area, total area of the heat exchanger, AT we can, A or AT we can take from this one, UDA. Then this integration 0 to A, U we are going to get, dA will be A. Then if you substitute AT minus x AT, UM we are going to get, UM is the mean overall heat transfer coefficient, average or mean overall heat transfer coefficient. This whatever is there, this will get ln of delta T after integration. Ln of delta T within the limits, if you take that one, ln of delta T naught by ln of delta Ti. Ln of delta T naught minus ln of delta Ti will get, that simplification we are going to get as a ln of delta T naught by delta Ti is equal to minus x UM AT. Then if you again rearrange this one, negative sign, if you take this side, we are going to get as a ln of delta Ti by delta T naught is equal to x UM AT. The total heat transfer rate Q through the heat exchanger is determined integrating equation 6 over the entire length. The equation 6 whatever we have taken, that is a d of delta T is equal to minus x dq. Okay, this if you integrate within the limits, that is delta Ti, delta T naught, d of delta T is equal to minus x 0 to q dq. This we are going to get as a delta Ti minus delta T naught, and this, okay, this we are going to get x into q, and q we can write as a delta Ti minus delta T naught. After simplification, the q we can write this delta Ti minus delta T naught. Then here this x value whatever is there, x will if you take from this equation, that is x is equal to ln of delta Ti by delta T naught by UM AT. That if you substitute in this equation, okay, then ln of delta Ti by delta T naught by UM AT, that is taken into the numerator. The q we can write as a delta Ti minus delta T naught by ln of delta Ti by delta T naught. But the total heat transfer rate through the heat exchanger in terms of the log mean temperature difference, LMTD, that we can write as a Q is equal to UMAT LMTD. That LMTD is the delta Ti minus of delta T naught by ln of delta Ti by delta T naught. This equation whatever is there, this is the logarithmic mean temperature difference. This whatever the rate of heat transfer is there, that we can have this one logarithmic mean temperature difference method of the analysis of heat exchanger. In particular special case, the one thing, this the directly Q we are going to get the rate of heat transfer, UA delta T LMTD we are going to get. From that heat transfer we can find out. Alternatively we can find out overall heat transfer coefficient also. And here special case, when delta Ti is equal to delta T naught, this term delta Ti is equal to delta T naught, the LMTD becomes indeterminate, 0 by 0 becomes indeterminate. Then applying the L'Hospital's rule, we are going to get it LMTD as a delta Ti is equal to delta T naught. Here it is very important, delta Ti or delta T naught, any one which I have take, if it is a delta Ti is equal to delta T naught as a LMTD. Okay, then the arithmetic mean temperature difference also we are going to get. Then this mean temperature difference method, there also LMTD or AMTD we can substitute. And here for parallel flow, delta Ti is equal to Thi minus Tci, delta T naught is equal to Th naught minus Tc naught. This is for the parallel flow heat exchanger, and for counter flow heat exchanger I will take in the next class. Thank you.